a flying vehicle about 243 feet long, capable of moving over the water's surface at a speed of 310 miles per hour, is known as the Project 903 Loon Ekranoplan. Moving at a height of just a few feet, it carried 6 launchers for anti-ship missiles on board. This Soviet development was the result of lengthy engineering research in the field of creating specialized technology. The appearance of this model attracted close attention from Western military experts. After analyzing the images they obtained, specialists noted that the object combined the speed characteristics of jet aviation with the firepower of missile ships, while possessing specific operational capabilities distinct from the traditional fleet and aviation. The history of creating such machines in the Soviet Union began at the Central Hydrofoil Design Bureau, where engineers investigated the ground effect. This is a physical phenomenon where a cushion of air between the flying vehicle's wing and the water surface creates additional lift. The technology allowed the craft to move directly over the water with high fuel efficiency and develop speeds unavailable to displacement vessels. It was assumed that such technical characteristics could significantly influence the tactics of naval operations, since flying at ultra-low altitude made the Ekranoplan barely noticeable to most radar systems of that time, reducing the probability of early detection. The development was based on experience gained during trials of the experimental KM vehicle, known in foreign sources as the Caspian Sea monster. This prototype proved the fundamental feasibility of creating heavy ekranoplans and helped to identify technical aspects that required adjustment. Based on a detailed analysis of flight data and the design features of its predecessor, a new strike ekranoplan was designed. Project 903 received a power plant consisting of 8 NK87 turbojet engines with a thrust of 29,300 pounds-force each. The units were mounted on special pylons in the nose section of the hull. Swiveling engine nozzles provided thrust vector control, which contributed to maneuverability. With all units running, the total thrust exceeded 220,000 pounds, allowing the machine to take off from the water surface. The hull design included 10 watertight compartments to ensure the craft's buoyancy and survivability. The internal volume of the 3 decks accommodated necessary equipment, control systems, navigational instruments, and crew stations. To perform water landings, a hydroski device with shock absorbers was mounted under the hull to reduce impact loads upon contact with the surface, which allowed the craft to operate in sea states of up to 5 or 6. The dimensions of the ekranoplan were a wingspan of 144 feet, a length of 242 feet, and a height of 63 feet. The main armament of the Loon ekranoplan consisted of 6 Moskit anti-ship missiles located in 3 twin launchers on the upper part of the hull. These missiles were classified as effective anti-ship systems, and their placement on the ekranoplan was intended for striking carrier battle groups with the ability to quickly exit the kill zone before return fire could be organized. Cruising at 217 to 250 miles per hour at ultra-low altitude made the ekranoplan less vulnerable to the air defenses of that time. Development of the Moskit anti-ship missile began in 1973 at the Machine Building Design Bureau, aiming to create a weapon with high-performance capabilities. A key design feature was the 3D-83 ramjet sustainer engine. A solid fuel booster was placed inside the combustion chamber to accelerate the missile to the ramjet's operating speeds. Once the fuel was spent, the booster was jettisoned, and the flight continued on the main engine just feet above the water, at speeds over 1,550 miles per hour. Since the Moskit complex was originally designed for surface ships, it was installed on the Project 956 Sovremenny-class destroyers in the early 80s. These ships gained the ability to strike targets at significant distances. The specific nature of the Ekranoplan, occupying a niche between maritime vessels and aviation, required an adapted version of the missile with its own launcher. Engineers had to account for basing, takeoff, and landing, as well as the need to fire missiles while in ground effect flight. By the late 80s, facing economic difficulties, developers proposed an aviation version of the Moskit to equip combat aircraft and expand the weapon's scope of application. A missile with such characteristics could have boosted the strike capabilities of naval aviation and long-range bombers. However, this project was never realized due to military budget cuts and the conversion of the defense industry. By the end of the 80s, testing was completed on the modified 3M80E missile, which featured an improved sustainer engine using more efficient fuel. This extended the weapon's range to over 62 miles. The integration of missile armaments for the Ekranoplan began with drop tests of weighted mock-ups at the Peshchanaya Balka testing grounds near Feodosia in October 1984. Specialists and engineers from the Design Bureau studied the behavior of these mock-ups in detail as they were dropped from ground rigs, analyzing flight trajectories and the functioning of separation systems. Every stage was recorded using cameras and measuring instruments. The data obtained was processed to make adjustments to the design of the launchers and control systems. Only after successful testing was permission granted to mount the missile systems on board the Ekranoplan. Aside from missiles, the vehicle was equipped with 2 artillery mounts, each fitted with 23mm double-barreled automatic cannons. These guns were the same type used on transport aircraft, which simplified ammunition supply and technical training. The high rate of fire allowed them to create a dense barrage capable of countering anti-ship missiles or low-flying targets. The artillery systems could engage both air and sea objects, providing close-range defense. A significant design feature of the machine was not just the missile armament, but the specific placement of the propulsion system in the nose section. This technical solution was dictated by the location of the anti-ship missile launch containers on the hull and safety requirements during firing. If the engines had been placed in the tail section as standard, the combustion products from the solid fuel boosters during a missile launch would have been sucked into the air intakes. This would cause a compressor stall, potentially leading to engine stoppage or damage. Positioning the engines at the front eliminated this risk and ensured safety during launches. To ensure operational effectiveness, the Ekranoplan was equipped with powerful radar stations responsible for navigation and target designation in any weather conditions. These stations made it possible to detect surface objects at significant ranges, track their movement, and transmit coordinates to the fire control system. Operators could simultaneously track multiple targets and prioritize them for destruction, which allowed for attacking a group of ships in a single sortie. The radar equipment was housed in special fairings that protected the electronics from the marine environment and physical loads. Construction of this craft began at the Volga experimental plant in 1983, during a period of intense activity in the defense industry. Thousands of engineers, technicians, and workers were brought in to create this complex machine, which possessed characteristics that were unique for its time. The Ekranoplan was assembled in a massive production hall, where work on various nodes and units was proceeding in parallel. Specialists welded aluminium alloy sheets, laid communication lines, and installed control systems. Every structural element went through technical quality control, which was essential to ensure component reliability and operational safety. The craft was launched on July 16, 1986, with the plant's employees in attendance. The machine left the slipways and entered the water, after which it faced a program of mooring trials that included checking systems and mechanisms, as well as tuning the engines and electronics. Once this stage was complete, the Loon was sent to the Caspian Sea for flight tests and to verify its technical capabilities in conditions close to actual operation. Testing on the Caspian began in 1989 and revealed the need for further fine-tuning of this technically complex product. The Ekranoplan demonstrated impressive flight performance, stability in ground effect during various sea states, and good controllability. The crew focused on mastering the machine, practicing takeoffs, landings, low-altitude maneuvering, and turns. The experience gained allowed them to move on to the next stage, missile testing. The first single launch of a Moskit missile ended in an incident. A malfunction occurred in the control system during launch, causing the missile to deviate from its calculated trajectory and fall into the water without reaching the target. A commission analyzed the telemetry and system performance to identify the causes of the failure. The engineering staff checked electronic units, connections, and software. The future development of the project, in which significant funds had been invested, depended on the results of this investigation. After the fault was found and fixed, preparations for retesting began. A two-missile salvo against the target was successful, confirming the Ekranoplan's ability to perform combat missions. The missiles launched a few seconds apart. Their engines powered their flight to the target at a low altitude above the water's surface. Observers recorded the wake of the missiles, their maneuvers while closing in on the object, and the direct hit. The practice target, a decommissioned ship, was destroyed by the impact of the warheads. The test participants evaluated the firing results positively. That same year, 1989, the craft completed state trials, confirming that the Loon's characteristics met the stated requirements. The maximum speed was 310 miles per hour, practical range was 1,240 miles, and flight altitude in ground effect was between 3 and 16 feet. Seaworthiness was rated at sea state 5 to 6, which allowed it to operate in significant waves. The wing area was 5,920 square feet, and the empty weight of the craft was 268 tons. The 10-man crew included the commander, navigators, radar operators, flight engineers, and weapons specialists. From 1990 to 1991, the Loon underwent trial operation as part of a naval unit on the Caspian Sea. The crews practiced tactical maneuvers with the Ekranoplan, coordinating with other fleet forces and running mock attacks on target ships. The vehicle demonstrated impressive technical capabilities. Navy representatives saw great potential in this new type of weaponry. There were predictions that further development and mass production of these machines could shift the very nature of naval operations. However, political and economic events began to move rapidly, sealing the project's fate. The collapse of the Soviet Union at the turn of the 90s triggered a crisis in the defense industry, slashing military orders and forcing a conversion of production lines. Factories that once built weapons had to switch to civilian goods, and funding for many advanced military projects was simply cut off. The Lund project faced a total freeze on the government funding needed to maintain and operate such unique machinery. But taking this combat vehicle out of service wasn't just about budget deficits, it was also a strategic shift. Fleet Command was unsure how to use the Ekranoplan in the changed geopolitical landscape. With the end of the Cold War, destroying aircraft carrier groups was no longer a priority. Military planners had no clear concept for how these machines fit into the new security environment. On top of that, operating them required specialized infrastructure and personnel training, tasks that seemed nearly impossible in the economic climate of the time. Nevertheless, the developers tried to save the program. In 1990 and 1991, they ran a series of live tests with the existing model to see if the Ekranoplan could handle search and rescue operations in the open ocean. The results confirmed the machine was effective for civilian use. Its speed allowed it to reach remote disaster zones quickly, evacuate people from sinking ships or oil rigs, and deliver rescue equipment and medical staff right to the scene. The combination of rapid response speed and heavy payload capacity made the Ekranoplan a viable option for extreme rescue scenarios. Based on the test data, engineers drew up plans to convert the combat vehicle into a specialized vessel named the Rescuer. The design called for stripping out the missile systems, significantly altering the interior and installing equipment to evacuate survivors. The second unit in the series, which was still under construction at the Volga plant, was chosen as the base for this civilian version. Work began despite the factory's dire financial situation and no guarantees of payment. According to the blueprints, this rescue Ekranoplan was designed to transport anywhere from 150 to 500 people, depending on the cabin configuration. When evacuating the severely injured, the vehicle's capacity dropped because space was needed for medical stretchers and to ensure doctors could access every patient. In cases where the goal was to take people off a distressed vessel without the need for urgent medical care, the maximum number of evacuees could be taken on board. The design envisioned a full-fledged hospital with an operating room for performing emergency surgery and flight, as well as an intensive care unit with life support equipment to transport critically ill patients to shore-based centers. The 7 members of the main crew were stationed in the forward cockpit, where the controls for the Ekranoplan systems were concentrated. The commander and co-pilot sat side by side in front of the instrument panel. The flight engineer monitored the power plant, while the navigator was responsible for the route and navigation equipment. In the tail section of the craft, a cabin was outfitted for the navigator-operator and a team of rescue workers, whose job was to coordinate evacuation efforts. An observation post was set up at the top of the tail fin, providing a wide view to visually spot people or objects in the water from a significant distance. This position was crucial for searching during low visibility or at night. The project was brought to a halt due to a lack of funding. The state budget was in a deficit, and existing funds were being redistributed to pay salaries and pensions. The question of finishing the Ekranoplans took a backseat, despite their life-saving purpose. Potential government customers, like the relevant ministries, didn't have the budget to purchase and maintain such expensive machinery. Commercial entities didn't consider investing in the project because rescue operations don't generate a direct financial profit. The Spasatel craft remained unfinished on the slipways, and work on it ceased as the enterprise plunged into crisis. There were no alternative options to convert the strike craft for civil use because of the specific design features of the Loon. The Ekranoplan was designed from the start as a platform for anti-ship missiles, and its layout just wasn't meant to be retrofitted for regular cargo or passenger transport. The combat Loon Ekranoplan continued to operate on the Caspian Sea within the limits of available funding and technical resources. Crews flew training missions, practiced coordination with surface ships, and kept the weapons systems combat-ready. However, over time, it became clear that maintaining a single unit of such a complex machine made no economic sense in the middle of an economic crisis. Spare parts for the engines and electronic equipment were running out, and new supplies weren't coming because the supply chains had been broken between factories that ended up in different countries after the collapse of the USSR. The technical staff tried their best to keep the machine operational, fixing malfunctions despite a severe shortage of components. The technical crew kept swapping out components, moving parts from one system to another to keep critical elements operational. With no original spare parts available, they had to come up with alternative technical solutions. Specialists often worked overtime, striving to keep this complex mechanism functioning. However, as the service life ran out, continuing to operate the craft was deemed too risky for the crew. Command decided to stop the flights, seeing no point in using worn-out equipment given the uncertain future of the entire Ekranoplan program. The decommissioning of the Loon happened as a standard routine, with no public attention or official ceremonies. After its final flight, the Ekranoplan was parked in a bay on the Caspian Sea, waiting for a decision on its future status. In the years that followed, the structure naturally began to decay under the influence of the sea and the climate. Metal corroded, coatings peeled away, and the internal compartments fell into disrepair. The object became part of the coastal landscape that locals got used to, and it only occasionally caught the eye of visitors as a technical curiosity. The second unit in the series sat unfinished at the Volga plant facilities, effectively becoming a monument to unrealized plans to convert the military project into a rescue vessel. The massive hull took up factory floor space that could have been used for other things, but for a long time, the plant staff couldn't bring themselves to dismantle it. There was a belief that the economic situation might stabilize, which would allow them to find the resources to finish assembly. Nevertheless, decades passed, and construction never resumed. The fate of the Loon Ekranoplan became a clear illustration of how complex engineering developments can end up unwanted due to a shift in political and economic direction. The machine the engineers created boasted high performance and powerful weaponry, but these achievements lost their relevance after the collapse of the state that initiated these projects. Foreign experts continued to analyze the experience of designing heavy Ekranoplans, studying the developers' achievements, but the creation of direct functional counterparts to the Loon never became widespread in other countries. This particular model demonstrated that the engineering school of that period was capable of solving non-trivial design challenges and creating types of machinery without precedent in world practice. Theoretically, the presence of such craft could have influenced the strategic balance of power in naval theaters, but the program was shut down due to external circumstances. This project has gone down in history as an example of the production capabilities of the past defense industry and a demonstration of technological potential that was never fully realized because of massive geopolitical transformations.